So last time we did the derivative, and now we're going to do the integral. Short version, you just do the exact opposite. Okay, there's some more detail than that. So I drew here a velocity versus time graph. And y'all know from previous work that if I want to know the displacement, I need to find the area of this graph. So if I sketch in, this is a triangle, I can color it in just to show what I'm doing. So the area is 1/2, the base is 6, the height is 10, so this is a displacement of 30 meters. You all know how to do that at this point. But what if I give you a more interesting velocity function? This is a boring one. This object is speeding up at a very constant rate. This is somebody driving an interesting car. So they're speeding up, they slow down, they speed up more. They're speeding up at about the same rates. So these are similar accelerations. They're slowing down slower. Why are they doing this? Who knows? Maybe it's along with the beat of the music. Dum, da-dum, da-dum, whatever. Just go with it. But this is the velocity function. For some reason, someone is driving like a crazy person like this. Or maybe it's a roller coaster. I want to know the displacement. So if we want to know the displacement, we've got to do area. Well, how do you do this area thing? And let's just go with the total. Forget the different sections. But so, well, I was speeding up to here. So that's pretty much a triangle. And then when I slow down here, it's close to a triangle on top of a rectangle. And then I've got close to a triangle on yet another rectangle. But that's not a triangle. That's a curve. In fact, if we sketched in where the triangle part would be, our triangle area would miss all of this. And so this would not get the total area. It would miss some parts, it would probably overdo other parts. So someone came up with an idea, and I don't know if this exactly was Newton, whoever came up with this idea of saying, instead of doing all these funky different shapes, let's make this a process we're going to do over and over and over, iterative process. So on this same graph, same motion, I have broken the time axis into 6 equal parts. And so if I use a ruler and draw up each of these, you can see, and we're going to do, I could make a collection of rectangles. So instead of calculating the area of a bunch of different shapes, triangles and triangles on top of rectangles and everything else, all I have to do are rectangles here. But I do have a problem. I've got a little bit of over area here, over here, over here. I'm missing area right here. I'm over here, I'm over here. And there are ways to adjust this. We could make this the midpoint of the rectangle. Or we could do more rectangles. So on this one, I'm not going to use the ruler this time. Instead of 6, I broke this one into 12. So after I draw these in, whee! Now when I do my rectangles, they're a lot closer. And I guess it should be more like that. If I go even wilder, I can do, this is with, okay, this could take a minute. This is 24 rectangles. Whoa, that one was so not vertical. Okay. You know what? I think I'm going to stop on this first half. But you can see as I draw the rectangles in, that these rectangles are closer and closer approximating the area of this. Now I want to fill them in because I want to have the whole visual impact. Wow. Okay, so for those of you who looked at the printed notes, you know this is a lot prettier because I used a website to generate those pictures. And it actually had in the last picture, I believe, 40 rectangles. But you can see the difference across this progression. I'm always doing rectangles. These rectangles have a lot of overage and unders. This has less overage and under. It's better. This is even better. I can do more and more and more and more and more, but that's a lot of rectangles to calculate. However, it's a fairly easy process because we're always just calculating what's the area of this rectangle and this rectangle and this rectangle. And this lower part, this is the time interval. It's the same all the way across. So it's always half a second times the height, half a second times the height, half a second times the height. So it's a different velocity every time, the height, but the width is the same. So to switch to some symbols, what we've been doing here is approximating the displacement by adding up. Remember, this is the summation symbol for math class. It means add it all together. We want to multiply the height of the velocity function, whatever that curve is, times the width of the time interval. Rectangle, area, base times height. In symbols, we would write this as add up all of the velocities times the time interval. So at each individual one times the associated time interval. And if we do smaller and smaller delta t's, we would write that as the limit as delta t goes to 0, which is exactly what we had in the derivative function. So, oh, that wasn't quite on the screen. So now I'm going to turn the page. And this is where the magic comes in. We are going to say that our position function is equal to the limit as that time interval, the base on all those rectangles, goes to 0. It gets smaller and smaller and smaller, of this velocity times the width of the time interval. This then turns into an integral of the velocity with respect to time. So notice the matching parts. We had summation. We were adding up a bunch of rectangles. Notice the integral sign looks like a big S. That's on purpose. It means summation still. It's just a fancy sum. Integration is just a fancy way of adding stuff up. We have the velocity function. We have the velocity function. That's the height of the thing we're doing. And when we were calculating width of the rectangle, it was important to know how wide that rectangle was on the bottom. Well, it doesn't have any width anymore. It's become vanishingly skinny, but we still have to remember that we are integrating with respect to time. So dt is always going to be here to tell you how you're integrating. Eventually, there are things called multivariable calculus, so you might have a function of x and y and z. So do you want to integrate this time along the x-axis or the y-axis or the z-axis? But that's the second year of calculus, so don't worry about it right now. And there's one more part, plus c. I was talking before about displacement, and now I've gone to total position. Well, sometimes you start from someplace. You don't start from 0 always. So this is the initial position. At time t equals 0, where was this object located? I did this, I skipped a step here that I would have done. I would have done just the displacement, would have done displacement in here, but the written notes match this, so it all works well. So if you were in calculus, you'd spend some time actually calculating the sums of all those rectangles on the previous page, and then you'd get here, and then you would do a lot more stuff, and finally you'd learn the shortcut. So we're going to skip ahead to the shortcut. If your velocity function is given by a t to the n, then your position function, which is the integral of the velocity with respect to time, that's how you read that, the integral of velocity function with respect to time. And so we're doing the integral of a t to the n dt. We keep the coefficient, we raise the exponent by 1, and we divide by the new exponent. And then we write plus c, meaning plus a constant. So again, we keep the coefficient, raise the exponent, and divide by the new coefficient, excuse me, the new exponent. As opposed to, I want to contrast that to, remember the derivative formula. Derivative, sorry. If you knew that x of t was the same a t to the n, then v of t which was the derivative of x with respect to time. We multiplied by the exponent and then lowered the power by 1. So with the integral, we raise the power by 1 and we divide by the new exponent. With the derivative, we multiplied by the old exponent and lowered the power by 1. So now let's use it. Sliding up the notebook, keep the formula on the screen. So example, if we have a velocity function given by a rather long formula, plus 4t plus 2, we want to find x of t. So we apply this formula to each of the three parts. So x of t equals 3 times t, add 1 to the 6th, divide by the new exponent 6, plus 4t, there is an implied 1 here. So we add 1 to get 2, divide by the new exponent 2, plus 2 is a constant. There is no t here, which means there is an implied t to the 0, because t to the 0 is 1. There's no variable. So we keep the 2, and we raise 2 to the first power and divide by the new exponent. And then don't forget the plus c, which means the initial location. And now we simplify this. So 3/6 is 1/2 t to the 6th plus 2t squared plus 2t plus c. Now, I personally really like doing derivatives, don't so much like doing integrals, even though they are opposites of each other. So I always check my work. When I finish a position function, I check myself with the derivative function. So remember, derivative, you multiply the exponent and the coefficient and lower it by 1. So if I do 6 times 1/2 times t to the 5th plus 2 times 2 t to the 1st plus 2 times 1 t to the 0, and then this is a constant, so its derivative is 0, we'll simplify this. This is 3t to the 5th plus 4t plus 2, that's just 1, and that's what we started with. That's the original function. So when we integrate and then take the derivative, we get the exact opposite. We get the exact same thing back, because doing the integral and doing the derivative are opposites of each other. So that's the check on our work. So most of the time, we don't just want to leave a plus c. Most of the time, we want to know about that. So let's say you were given another condition. So continuing this. An additional piece of information is that at t equals 2 seconds, x was 10 meters. So I can use this to solve for plus c, because when I put 2 seconds into all of this, I'm going to have c as a variable, but it's got to be equal to 10 meters. So I'm going to plug it in. X of 2 equals 1/2 times 2 to the 6th power plus 2 times 2 squared plus 2 times t plus c, all has to equal 10. Okay, 2 to the 6th, I'm not in the mood. 2 to the 6th is 64, half of that is 32, plus 2 squared is 4 times 2 is 8, plus 2, what, I didn't put the 2 in, shame on me, plus 2 is 4, plus c equals 10. So 32 plus 8 is 40, plus 4 is 44, 44 plus c is 10, subtract 44 from both sides, c is negative 34. So the real velocity function, including this extra piece of information, is that x of t equals, we're not quite on the screen, 1/2 t to the 6th plus 2t squared plus 2t minus 34. And that's the answer you would enter in the Schoology. Okay? So, one more problem type to do as an example. Let's start with a different function. So I'm going to give you that the velocity of an object with respect to time is given by 8t cubed. And I would like to find the displacement between t equals 1 and t equals 5 seconds. So this is going to be a slightly different integral. The one we just did, I should have turned the page before I said this. The ones we were just doing, this here is called an indefinite integral. It is not definite because of this plus c over here, because you actually have, this is a million answers. If we go down to the one we did, there are an infinite number actually of position functions because each one of them has a different intercept. So if we want to do displacement, we don't really care about the starting point because we would find the location at one point, the location at the other point, subtract them to find the displacement. So it doesn't actually matter where we started. So now we're going to do something called a definite integral. So it's going to be set up slightly differently. Delta x is the integral between the two times of the velocity function integrated with respect to time. So for this problem, because I think the example illustrates it best, I put the two times in order. So 1 to 5, 1 goes on the bottom, 5 goes on the top. And then I copy my velocity function, 8t cubed, and I'm integrating with respect to time. So first job is to integrate this expression. So keep the coefficient, raise the power by 1, and divide by the new power. And I'm not going to write plus c. I'm going to make a bracket. I'm going to fill in 1 and 5. I'm copying. So I'm going to simplify this. This is 2t to the 4th. Copy my bracket, 1 to 5. And now I'm going to evaluate this answer at both of these endpoints, and we're going to subtract them. Because essentially what we're doing is when we put 5 in, we are finding the position, the location at 5 seconds. When we put 1 in, we're finding the location at 1 second, and we subtract them to find the displacement. This is one of the, I think this is the second fundamental theorem of calculus, that the total area between 2 points is given by the difference in the integral between those two locations. So 2t to the 4th, so I'm going to do 5 to the 4th power, and then I'm subtracting the same function but evaluated at the other endpoint. So yeah, 5 to the 4th, is that 625? Yay me. So 2 times 625 minus 2 times 1, so, okay, yes, I used the calculator. 250 minus 2, so the displacement in this problem is 1248 meters. Okay, so that's a lot of calculus in one lesson, but we're doing great. You are doing great. You're going to do fine.